I guess a couple of brief announcements. So homework number 4 is out, has been posted on Monday, and I guess Willie has homework number 1 graded around here, so you guys can pick it up. Great. So today we're going to continue to talk about sample complexity results. So we've already seen this several times. Okay, what's going on with my? Okay, just a second. Okay, cool. So I've already seen several times in the course that the two key questions that we care about in supervised machine learning are the algorithm design question. How can we design computationally efficient algorithms that do well over the training set? So this is question number 1. And the question number 2, and this is the focus for last lecture, and the question number 2 is a sample complexity or confidence bounds or generalization guarantees question, which is asking how many samples do we need in order to be confident that the rule that does well over the training set will also do well in the future. So in other words, how many samples do we need in order to not overfit? Okay? And we talked about this last time, and and as I mentioned last time, in order to even ask this question, we need to have a precise model, right? And the model that we talked about is a classic distributional learning setting, which is captured by the statistical learning theory framework of Vapnik and the PAC model of Valiant. Okay? And I'm just going to very briefly, in 3 minutes, review what we discussed about last time, and then go on from there. Okay, so in this model, so I guess for my class today, I'm going to focus on supervised classification, where the label space is discrete. Even think about it as being binary for today's lecture. Okay, so we are thinking about classification problems, for example, of the type we want to classify email messages as being spam or not spam, or some other image classification tasks, and so on. So, and the model that we have in mind is as follows. So, in these distribution learning scenarios, we assume that there is some underlying probability distribution over the space of unlabeled examples. So in other words, all our examples come from some source, right? So we have some distribution over the space of unlabeled examples, for instance, over the space of email messages if you want to do spam detection. Okay, and in the training phase, first a random sample, a small random sample of these examples are labeled by an expert, for example, as being spam or not spam for the spam detection problem. And then this random sample is given as an input to a learning algorithm, which then produces a hypothesis function or a classifier that is then used to classify new subsequent examples that would come from the same underlying source. Okay, right. And what my classifier might output, say, it could be like a linear separator. Right, or my algorithm might output could be like a linear separator in the case of logistic regression, or a decision tree if it's the ID-free algorithm, and so on. Right, so that's pictorially the model. So let me write it also a little bit more formally. So in this model, so assume that we have a feature space, right? So for example, it can be Rn. So we have a feature space, and we have a distribution D over the feature space. And we assume that in the training phase, first a small sample, random sample, drawn random from this distribution, is labeled according to some fixed but unknown target function. Okay, so here the distribution D is fixed but unknown, right, over the instance space. And we assume that in the training phase, basically we first get to see a small random sample, so we get to see examples of the form x1, label of x1, x2, label of x2, and so on, xm, label of xm. Right? And we assume that all these examples xi are drawn independently, and they're identically distributed from the underlying distribution D. So there are ID examples. Okay? And we also assume that they are labeled according to some fixed but unknown target function C star. Okay? And the goal, I mean, what the algorithm can do, obviously, it can just do some optimization over the given sample. But the true goal of the learning algorithm is to output a hypothesis function that does well on new examples that come from the same underlying source. Okay, and so formally, we discussed about this in detail. What we care about is outputting a hypothesis function H that has small error rate with respect to the underlying distribution and the underlying hidden unknown target function. Okay, And by notion of error, we just mean this very classic zero-1 error or classification error loss, which is just defined as the probability that my hypothesis H predicts differently from the target function on an example that comes at random from the same underlying source. Right? And we saw that pictorially, we can think about it that way. Okay, so that's the true goal, to output a hypothesis function that has small error rate with respect to the hidden unknown target function and the underlying distribution. Now, we also discussed this in detail last time. In order to hope to achieve any generalization, in order to hope to do any learning, right, with a small number of labeled examples, we need a bias, because there is no free lunch. Like, we can never get something for nothing. And within these frameworks, within the statistical learning theory framework or the PAC model, the bias is expressed through a hypothesis space H. Right? So what we imagine is that we imagine that we are fixing a hypothesis space H, like linear separators or decision trees or your other favorite hypothesis space, right? And then the implicit hope is that somehow the target function is close to some function in the hypothesis space. Okay. And actually, there are two cases to think about. So the first case is the simplest case from a, I guess, formal point of view. It simplifies the math quite a bit. So the simplest case where we assume that we have been so insightful that indeed the target function belongs to my hypothesis space. So that's called the realizable case. Okay, and then in that case, right, so that's a simpler case. And the case where the target function does not belong to the hypothesis space, that's called the agnostic case. But even then, the implicit hope is that the target function will be close to some function in the hypothesis space, because this will only be our search space. Okay. And we also talked about this, for this hypothesis, for this bias to be useful, we need to ensure that somehow the complexity of the hypothesis space H is not too large. If H contains all the functions in the world, then this is not a very useful bias. So we're going to fix a space H whose complexity in a certain sense is not too large. Okay, cool. So that's the formal setup. Now, again, so recall, we'll use labeled samples drawn at random from the underlying distribution, right? Labeled according to some fixed but unknown target function. And our goal is to output a hypothesis function that does well on new examples that come from the same source. Now, right, I want to output a hypothesis function, small error rate. And again, we discussed this last time. Obviously, because we don't know the underlying distribution and we don't know the target function, there is no way for us to actually measure the error rate of a given hypothesis precisely. Right? That's something we cannot compute precisely. But instead, what we can do, we can compute the empirical error or the training error of any given hypothesis function. So the empirical error is formally written on the slide, right? And it is defined as, anybody volunteers? So what is the training error of a hypothesis? It's written on the slides, but maybe somebody can help me out. What is the empirical error of a hypothesis H? Just to make sure. The training error. Yeah?
It is the number of samples that, so we are trying to, we have the training set.
Sure.
And we know the label for them.
Yeah.
Then we do that, we check that with hypothesis. So we see how many of the labels are predicted not correctly.
Exactly. So and we normalize it by the number of training samples, right? So we get a fraction. So training error is just the fraction of misclassified examples with respect to the hidden target function. Okay? Yes?
I think your mic is cutting out when you go to the other side of the room.
What happens?
I think your mic is cutting out when you go to
Okay, good. So maybe I should stick around here. I'll try. See if it's possible. Okay, cool. So, right, so to really care about is outputting a hypothesis function that has small true error rate, but we cannot measure that. Instead, what we can measure is the empirical error rate of a hypothesis, which, as Mustafa said, is just, so the empirical error of a hypothesis is just the fraction of training samples that our hypothesis misclassifies. Okay, so we can measure the training error, and but our true goal is to guarantee something about the true error. And so actually it turns out in order to do so, we can use sample complexity statements. So what sample complexity statements help us do is to relate the empirical error of a hypothesis H with the true generalization error of a hypothesis H. And moreover, they help us do so uniformly for all our hypotheses in the hypothesis space. Okay, so this is what sample complexity results can help us do. Yeah? Because if we're able to relate this, if we're able to somehow guarantee that these two quantities, the empirical error and the true error, are arbitrarily close, then we know if the number of samples is large enough as a measure of the complexity of the hypothesis space, then we know that if we optimize over the training sample, we'll also have good generalization error. Okay, cool. And so last time we've seen a concrete sample complexity result for the simplest case where the hypothesis space H is finite, and this sample complexity result that we talked about actually is only meaningful in the case where the target function itself belongs to the hypothesis space. So it's meaningful for the realizable case. Okay, and this was a sample complexity statement for a consistent learner, for a learner that simply just outputs a hypothesis that is consistent, that fully correctly labels a training sample. Okay. And so let me go through the statement again. So it's very simple to state, it's very simple to prove, it's super insightful. Okay, so what the statement says is that if the number of training samples we see is at least 1 over epsilon log size of H plus log 1 over delta, then with high probability over the draw of the training sample, so with high probability at least 1 minus delta, all the hypotheses in our hypothesis space that have true error rate at least epsilon will be inconsistent with the data. Right? So if we see so many training samples, then with high probability, all the bad hypotheses that could fool us, that have true error rate at least epsilon, will make at least one mistake over the sample. Okay? And so basically, if we then take the contrapositive, what we get is that if we see so many training samples, then what this implies is that if we see so many training samples, and with high probability, all the hypotheses that have empirical error rate 0, but are perfect, that perfectly classify the sample, will have true error rate at most epsilon. And so in the case where the target function indeed belongs to my concept class, then I'll be able to find something that perfectly labels the sample. And so if the number of samples I've seen is of this order, then I'm guaranteed that my generalization error will be at most epsilon. So I'm going to be doing great. Okay? So that's the statement that we discussed last time and we proved in detail. It was one slide proof, super insightful proof though. Okay, so cool. So, and we then discussed this bound in detail. We went through examples. And let me just mention what's essential here. What's interesting about this bound is that actually the dependence on the size of H is only logarithmic. Okay, that makes this bound interesting. Okay, because then we could have hypothesis space that are exponential in size, that have an exponential number of functions, but we only need a polynomial number of samples to learn well, to achieve generalization guarantees. Right? And that's an example we went through last time. For the class of conjunctions, we have exponential number of conjunctions, but the number of training samples we need in order to get error at most epsilon with probability at least 1 minus delta is only polynomial in n and 1 over epsilon. So which is very nice, because I mean, here both the instance space and the hypothesis space have exponential size, but what we can guarantee is that we only need a polynomial number of training samples to achieve good generalization, which is really interesting. Okay, cool. So this is just a recap from last time. And I also want to just show this again. So we're actually, so the same theorem, so this is more the PAC way to state the theorem. It stands for probably approximately correct, PAC. Again, because with high probability over the draw of the training sample, we want to be approximately correct, yeah? So this is the PAC way of stating the statement, and the way it's stated is in the form of how many training samples suffice in order to guarantee small error with very high probability, right? So this is the way I wrote the bound here is if the sample size is at least is large enough, then with very high probability, I can guarantee small error for all classifiers that are consistent with the data. Okay, so this is the PAC way of stating the result, and this is more the computer science way of thinking about it. Okay, now the more statistical way of thinking about it is written here. So you can rewrite basically, it's just just a rewrite of the same theorem. You can write the statement to say that no matter what is the value of M, so no matter how many training samples we have, we can guarantee that with high probability, at least a minus delta, uniformly for all hypotheses H that have that are perfect over the sample, so uniform for our hypothesis H that are consistent with the data, we have a bound on their true generalization error. So we have this bound, so the generalization errors decays linearly in 1 over m. Okay? So no matter what is the value of m, we have it uniformly for all hypotheses that are consistent to the data, that are perfect over the training sample, where generalization error decreases is of the form 1 over m log size of h plus log 1 over delta. Okay, so and this holds for any m, no matter what m is. I mean, obviously, the larger m, the better this bound is. And again, the key point here is that the dependence on the size of h is only logarithmic. Okay, cool. So that's just a recap from last time. All right, and like, I'm going to actually skip this, but just go and mention that last time we discussed that, okay, so this is a very insightful result. It's nice to prove, easy to think about. It's interesting. Now, however, it has two main drawbacks. One main drawback is that it's only meaningful for the case when the target function belongs to the concept space. Because if the target function does not belong to my hypothesis space, I might not be able to find something that is perfect over the training sample, right? So, and then we discussed ways to overcome this last time, right? When we talked about, well, we can give bounds, we can use a little bit of a different machinery, and we can give bounds that relate the empirical error rate with the true error rate uniformly for all hypotheses in the hypothesis space. Yeah, so this was discussed last time. So that's one, so we can fix that drawback. So we can make this bound hold for the agnostic case, where the target function might not necessarily belong to the concept space. Okay, but another main drawback here is that the hypothesis space H, I mean, the way the bound is stated requires that the hypothesis space H is finite. Okay, and obviously you guys know that for many of the algorithms that we care about, like logistic regression, the hypothesis space is not finite, right? So what type of classifiers is logistic regression outputting? What's the form of the boundary? Linear, yeah? So for linear, so logistic regression outputs linear classifiers, and there are an infinite number of them. So we cannot apply this bound, okay? So, but turns out, luckily, we can fix this problem. And so we can get very interesting sample complexity results, even in the case when the class of functions is not finite. Okay, and this is what I'm going to talk about today. And this is the more realistic case and the more interesting case practically, and also mathematically is like really cool. So, but I'm gonna present just the key insights. I'm not gonna go through the proofs. I'm just gonna try to present the basic concepts. Cool. So, any questions at this point?
Just point out the microphone is not working well in that side of the room. So.
Okay. Wow, that would be very hard for me to stay on one side. Okay, I'll try to stay here. It's a big constraint. Last time it worked on that side of the room, I think. I don't know what happens. It's maybe something with my, maybe I should just move. Maybe it's, is it better now?
It works really well when you close the podium.
Okay. Cool. So, well, if you guys cannot hear me, you should point this out. And also, if you don't understand what I'm saying, you should also point that out. So please ask me any questions. All right, so basically today we're going to talk about how can we state sample complexity results for the case when the class of functions that we are considering is not finite. Yeah, and this is really the most interesting and practically relevant case. For example, linear separators. So the class of linear separators is not finite, it's widely used. For my lecture today, just to describe the concepts, I'm going to use two other classes. These are more toy examples, but they are good for illustrating some of the basic concepts. So two other, yeah?
We have seen the graph between the error and the complexity of any hypothesis or any algorithm. Can you make it like a 3D graph where you add the M feature to it and then show it like how it varies?
I add which feature? The
M, the number of training samples.
The number of, so what are the two features? So, I mean, you typically show the graphs as a function of the number of training samples.
The training error keeps going down.
As you have more and more samples.
And the more and more.
The more and more the complexity grows as the complexity grows.
The training error, the testing error goes up again after one inflection point.
Okay.
Can you add another axis of n to it and show it like
Sure, I mean, you could.
Can you tell like how it will vary?
Yeah, so I guess the graph you're referring to, which I don't have on my slides, but the graph you're referring to, so if I have a fixed number of samples m, right, you are saying that the more I increase the complexity of the class of functions, the training error kind of go down. But on the other hand, the generalization error might go up. Right? It's typical, the typical behavior will go down and the eventual potential will go up, right? Yeah, so when you are saying now I want to unfix them too, and when you are asking how is that shape looking like, right? So now I fix them, and so.
Because like when we see the graph, it shows that training error is not it's not reflecting the true error in any case because it's going down and down, or the testing error is going up. So it's not reflective of the total error, the true error.
So the training error is not reflective of the true error. Okay, so let's come back to this question. So what I want to think about today, I want to think about a simpler question today. So like the type of bounds that we are talking about today. So okay, let's come back to your question because it's a more complicated question. But what I want to think about today, I want to fix a class of functions like linear separators, and I can still ask a meaningful question. Once we understand this question, we can then go and understand your question. Okay, but let's understand the simpler question first, which is I have a fixed class of functions like linear separators, and I'm curious to know how many samples do I need to see so that I can guarantee that uniformly for all linear separators, their true training error is close to their empirical error. Okay, so the first question is, can I even guarantee something like that? Because if I cannot guarantee something like that, I cannot even answer your question. There is no hope for me to answer your question. Okay, so for today, let me answer this simpler question. Okay, and we'll come back to that one. Okay, cool. So actually, thanks again. Thanks for the comment because I think it's basically the question that we are thinking about is we have a fixed class of functions like linear separators, and then what I want to know is how many samples do I need to see so that uniformly for all functions in my class, say for all linear separators, their training error is very close to their true error. Okay, and it turns out that there is a number of samples, there is a quantity that will ensure that. Okay, cool. So examples to keep in mind for today's lectures are linear separators, then thresholds on the real line, right? So these are toy examples, but I'm going to use this. So imagine that the classifiers here look like following. We have the real line is an instant space. There is just a point W, and everything to the left is labeled as minus. Everything to the right is labeled as plus. Okay, so this is almost like a linear separator in one dimension. Okay, and then we also have another example to keep in mind is the class of intervals. Okay, where basically it's, so we have two endpoints, and inside the interval AB, we predict positive, outside we predict negative. Okay, cool. All right, so now what can we say? So I'm going to start actually with a super quick high-level overview about how the construction will go, and then I'm going to go through details so that you can grasp the concepts. Okay, so let's go back to the case when the class of functions is finite, right? I convinced you last time that if the class of functions is finite, I can get the sample complexity bound by putting here log size of h, right? And where did this come from? Do you guys remember? Where is size of h coming from?
Coming from K.
Yeah, so we did inside K was the number of bad hypotheses. So somehow inside our proof, we did a union bound over all bad hypotheses that could fool us. Right? And we showed that if the number of samples is large enough, we're going to discard those by union bound argument. Now, of course, I cannot put here size of h because h is infinite, but it turns out that actually that even if the class is infinite, we can put a related quantity. So what we can put is a different number called, it's kind of the effective dimension. In how many ways, if I have endpoints, in how many ways can I label them with functions from my hypothesis space, right? So, and I'll go through this notion in detail in a minute, okay? So just right now, I'm just speaking at a very high level, right? So if the class H is very complex, contains all the functions in the world, then the number of ways in which I can label any endpoints is 2 to the m, right? However, if my class of functions at the other extreme contains only one function, I'm only going to be able to label those points in only one single way, right? So somehow we can think about this effective dimension, right? This quantity that I'm going to define in a minute, and it turns out, and this is quite interesting, and it's highly non-trivial, it's super cool to prove, turns out that we can actually put a bound, get a bound here, where we replace size of h in the finite case with this effective dimension when we have infinite number of classifiers in our concept space. Okay, so that's highly non-trivial. Okay, yeah?
So
I'll define this notion in a minute. So right now I just want to give a punchline of my, okay? So if you,
Maybe, I don't know, but I think it's a big picture question. So can we say that this kind of method depends on the learning
no.
method that we're using?
Yeah, so that's the cool aspect. They are very generic, right? Even the bound that we talked about for the realizable case, the generic sample complexity bound for the realizable case, apply to any consistent learner. So for any algorithm, as long as it outputs a consistent function, you'll be doing great. So that's the beauty of these results. They apply generically to many types of learning algorithms. Okay, that's why they are so powerful. Okay, cool. So I just want to spend just 1 minute on this slide because then I want to move on and actually go through this concept in detail. Okay, so let me say again, right? So when h is finite, we could use size of h here, log of size of h, and we could get our sample complexity bound. Now when h is not finite, it doesn't make sense, but it turns out that we can put a related quantity, which is the maximum number of ways of splitting endpoints with concepts from our concept class. Some sort of effective dimension of our hypothesis space, which captures how complicated that is. Now, if you look at this bound, it's not super pretty because it has m on both sides. It's very hard to think about what does it mean and so on. And so that's why it turns out that actually we can simplify it. So it turns out that we can basically relate this quantity h of m to a very nice and intuitive combinatorial quantity called the VC dimension of the concept class, which I'm going to define later. And then by using some very cool combinatorial argument, we can then argue that we can get a sample complex system that looks very nice and easy to understand. Okay, so when the sample complex system would be saying, if the number of samples we see in the training phase is d over epsilon times log 1 over epsilon plus 1 over epsilon log 1 over delta, then with high probability at least or minus delta, all the hypotheses that are inconsistent with the data, that are consistent to the data will have true error rate at most epsilon. Okay, so we can get a bound that looks very similar to the one that we have for the finite case, where instead of having log size of h, we're now going to have this VC dimension of h, notional dimension of h. Okay, so that's just the high-level picture. Now I'm going to go through this in detail, through the concept in detail. I'm not going to go through the proofs because they are really, really interesting, but it will take me a few lectures to present them, so I'm not going to go through the proofs, but I'm going to go through the concept. Okay, cool. So let me start slowly. Okay, so as I mentioned, so the key concept here is to think about this shattering, right? So this shattering coefficient or the effective dimension. Okay, and so I'll say in words what this is, and then I'm going to go through a few examples. Okay, so what is? So if we have a set of points S, we can think about the number of ways. So if we have fix a set of points S, and we can think about what is the number of possible labelings that my hypothesis space H induces on the set S. Okay, so, and for now, just to be clear, we are thinking about the binary case. So we're only thinking about binary classifier, plus, minus 1. So each point can be labeled in just 2 ways, right? So again, if I have a subset S of the instance space, I can think about H of S, which is what is a set of possible labelings that classifiers in my concept space can induce over the set S. Okay, and then I can take maximum over all subsets of size S. Okay, and here is actually, let's think about an example. Okay, so let's think about threshold classifiers, right? So this is a simple class of functions, right? And okay, so and you'll see in a second why this is so important, why this quantity is so important. Actually, let me say it now. Okay, so why is this quantity important? Well, because we could have many classifiers in our concept space, but as long as they behave nearly the same on my set S, this is what really matters, right? What really matters is in how many ways can my classifiers label my set of points? This is what it really matters when we do the sample complexity argument, when we do kind of the union bound, if you think about it, right? And this is what this quantity is exactly trying to capture. Okay, so let's think about this, I guess, again. So we are thinking, so just an example, we are thinking about these threshold classifiers that look like this. Everything to the left is minus, everything to the right is plus. Okay, and so let's assume that we have these 4 points. So the set S is given by the 4 points. Now, if I ask you guys, so let's assume that I have 2 classifiers. So this is classifier number 1, and this is classifier number 2. Okay, so what is the labeling that each of these classifiers induces over my set of points? Do I label the points differently, the same? What is the labeling? The same. And what is the labeling? So this will be minus. Yeah. This will be minus, minus, plus, right? So even if I have two different classifiers, they induce the same labeling over my set of points, okay? And now so this is the labeling. And now if I'm asking you, if I'm only allowing you to use threshold classifiers, so I restrict the class of classifiers that I can use, right? In how many ways can I label my 4 points? You said 5, right? Exactly. So the maximum number of, in principle, if you allowed me to use any class, any hypothesis, right? If I could use any function, then I could, in principle, I might be able to label it in 16 ways, 2 to the 4, 16 ways, right? But I'm only allowing you to use threshold classifiers. And as Mustafa said, this then implies that there are only 5 ways to label these points with thresholds. Okay, because basically I can put the threshold here. If I put it here, then I get the all positive, or I can put it here, then I'll get this labeling, and so on, right? So there are 5 places where I can put my classifier, right? And that will induce a different labeling of the set of points. Okay, this is for these 4 points. Now if I have m points, yeah, if I heard, m plus 1. If I have m points, m plus 1, right, for the same reason. So in general, if I have m points, if the points are distinct, if they're all different, yeah, then I get m plus 1. If some of them are identical, then I'll get fewer. But in the interesting case, I'm going to get m plus 1. And again, why? Because I'm going to have m plus 1 possible places, like here, 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 and so on, where I can put my classifier that will induce a distinct labeling. Right? Cool. So that's interesting. So, I mean, this quantity seems to be capturing a little bit, right, that this class of functions is a bit restrictive, right? So if I have given m points, there are only m plus 1 ways of, only linear number of, there is only a linear number of ways to label m points with concepts from my concept space, with thresholds. While in principle, if I allow an arbitrary search space, I could have 2 to the m ways. Okay, so something cool happens. So it seems to be like a good measure. Okay, let's look at a different example. Okay, so let's think about intervals on the real line. Okay, so if now, okay, good. So now the concepts look like this concept over here, right? That means everything inside is plus, everything outside is minus. Right now, in how many ways can I label m points with intervals? I'm happy if you tell me order of. If you are even more precise, it's good, but I order of, I'm fine too. Is it linear, quadratic, exponential, doubly exponential? 15, okay, I'll have to compute for this. You are telling me in the case of 4. Okay, how did you come up with 15?
Because
I'll have to plug in it to see. Okay, yeah.
because you replace the bar between the 2 points, and for every bar you have 5 choices. So that's 5 multiplied 4 divided by 2.
Okay, perfect. So it's like
Plus 5.
plus 1. Okay, exactly. Wow, you are very quick. Awesome. You are awesome. Good. So that was a super quick argument that we did for the case on M is 4, and I have it exact same argument on my slide over here, right? So if I have m points, right, in how many ways can I label those m points by using intervals? Well, I claim exactly as you said. I claim that I can do so in m choose 2, m plus 1 choose 2. Yes, the number of ways will be m plus 1 choose 2 plus 1. Right, so this will capture. So I'm going to have a special case when the interval is empty, where I place basically. Okay, let me try to use. Right, so I'm going to have a special case when the interval is empty. So then I'm going to place both endpoints in the same little part. Right, this is the plus 1 here. Okay, and in the other cases, what I want to do, what would happen, right? I would have m plus 1 options for the first part, and only m options left for the other part, and the order doesn't matter, right? So that's why I'm going to get m plus 1 choose 2 options. This corresponds to the case where I'll have at least one positive example, right? And this will correspond to the all negative labeling. Okay, exactly as you said. Okay, what's your name?
Terry.
Terry. Okay, that was very quick. Great. Cool. So, right. So for the class of intervals, now we get the number of labelings of m points with intervals is only m squared. This is basically quadratic. right? It's still much smaller than 2 to the m, right, which is again the maximum upper bound we could hope for, right? If h contained all the functions in the world, then the number of ways of labeling my point would be 2 to the m. And so in the case of intervals, we get something still much smaller, which is nice. It's only quadratic. But it's bigger than the case for, than the number of ways for the case of thresholds, right? Here we only had m plus 1. Oops, which is good because the intervals are more complex than thresholds. Cool. All right, so right. Okay, now why do we care about this quantity? Because, okay, so going back to our sample complexity result, because it's what we really care about. I'm going to come back to this slide later. So why do we care about this quantity? Well, we care about this quantity, right, h of m, right, which is the maximum number of ways of splitting of or labeling points of concepts in my concept space. Why do I care about it? Because it turns out we can provide a sample complexity guarantee that holds even in the case where the class of functions is infinite. Okay? And this sample complexity guarantee looks very similar to the one that we had for the case when it was finite, except when log of size of h, so ignoring constants, now log of size of h will be replaced by log of the shattering coefficient of 2m points. Okay? So it turns out that we can prove a result of this form. And the proof is super interesting. It's one of my favorite proofs. Whenever I think about it, I get very excited about it. Now, I don't have time to go through it, and also it's a little bit advanced. I'm just going to tell you, because you might be curious, I'm going to tell you a very, very high-level piece of intuition. It's just very, very rough idea. It's not quite right, but just if in case you are curious, why is 2m in here? Where is 2m coming from? I just want to mention, okay, how would you prove it? Again, again, it's super rough. It's not accurate. But where is 2m coming from? So the way you think about it is as follows. Is basically, so what we really care about is, and this is what we bounded last time, so what we care about is the bad event that there exists a hypothesis that is consistent with my training sample, but whose true error rate is at least epsilon. This is what I truly care about, right? And last time, for the case when h was finite, we bounded the probability of this bad event happening. Okay, this is what I truly care about. Now, it turns out that we can think about a related event. So S here is a true sample, it's a true training sample, right? And what I care about is bounding the probability of this very bad event be happening. Now, it turns out that there is a related event where now I have, in addition to my true sample, I also have a fake or ghost sample, okay, which is again also of size m and also contains elements drawn IID from the underlying source, from the underlying distribution. Okay? And now what this bad event B prime says is that, well, the bad event B prime is that there exists a hypothesis in my search space that is perfect over the training sample, but has error at least epsilon over the ghost sample. Okay? So that's an event that only involves two samples drawn ID from the same underlying source. Right? Now it turns out, and actually it's not very hard, but you have to verify and need to use some bounds. It turns out that actually, in order to bound the probability of the bad event that we really care about, it's sufficient to bound the probability of this related event that involves the true sample and the ghost sample, a fake sample, that we only have for conceptual reasons. Okay? And what's interesting about this fake sample, about this related event B prime, is that again, what we really care about here is the question is there a hypothesis that is perfect over the true sample, but looks bad over the fake sample? Now, why is this interesting? Because now, once I have, right, so here I'm talking about empirical errors in both cases, right? And so now I can think about, well, I care about the empirical error over the union of these kind of sets. And so now, kind of conceptually speaking, once I fix the set, these samples S and S prime, right? Once I fix these two sets of training samples S and S prime, there are really only a finite number of hypotheses that I care about. And in particular, what I really care about when I'm going to do my union bound is in how many ways can hypothesis in my hypothesis space shatter points in B union B prime, points in should be S union S prime here. I really care about the behavior of this hypothesis in the hypothesis space over the union of these two samples, of a real sample and a ghost sample. Okay. Now this is not quite done, because I mean what I'm saying is not quite right. Well, because if I do so, then if I'm not careful, there is no randomness left to bound the probability of a bad event happening. And so that's why the proof contains some other super cool tricks, like a symmetrization by random signs to then have some probability left to bound the probability of a bad event happening. Okay, so super, super quick, super high level intuition of the true proof. It's very deep and it's interesting. So I just wanted to mention why we would have here h of 2m. Because the proof itself as a first step goes from a bad event that relates the empirical error rate of a hypothesis with its true error rate, goes from this type of bad event that we truly care about bounding to an event that involves the empirical error rate of a hypothesis h over the true sample with the empirical error rate over a ghost sample. Now it's sufficient to only think about the behavior of the class h over the union of these two samples, S and S prime. Okay, and so that's all I want to say here. And by the way, this is just, I don't expect you to, I mean, it's okay. So this is just for intuition. You're not going to be tested on that, just if you're curious. Okay, what did I do? No. Give. I closed this by mistake. Okay, I just want to fix this because this is not right. It should be S union S prime. Because B are bad events. Okay. All right, so let's go on. Okay, so this was just a side comment. Oh, what did I do? I should just go to. Okay, cool. Right, so this was a side comment. Okay, so going back to the bigger picture, right, as I said, it turns out actually, so we can basically replace size of h, in the case when h is finite, to this quantity, the number of ways, the Shattering coefficient, the number of ways of splitting m points of concepts from my concept space when h is infinite. Okay, and that's very good because we already get a sample complexity result, even in the case when h is infinite. Okay, now, so that's progress. On the other hand, this quantity is hard to think about. So even, I mean, it's like, it's hard to think about. And moreover, the unfortunate fact is that actually in this inequality, I have m on both sides, right? I have m on the left-hand side and on the right-hand side, right? So it's not the cleanest result in the world. It's a sample complexity result. It's a progress, but it's not clean. What we really want is a sample complexity stemma that we can then understand and interpret in cases that we care about, like linear separators. Okay? And so luckily, it turns out that this is all done for us. So, right, we can do that. And so we'll be able to do so by using something called the VC dimension of a concept class. Okay, and to also motivate the VC dimension, let me just make one more comment here. So if we look at this bound over here, right, if the class of functions is large enough and it happens that my class of functions can shatter m points or can shatter 2 m points, right, that means, oh, did I define the word shattering? No, I didn't define it yet. Okay. So if my class is large enough so that basically it's able to label, say, 2 m points in all possible ways, right? Then that means that the size of h of m will be like 2 to the m, right? Or h of 2m will be 2 to the 2m, right? So in that case, right, if for a sample of size m, h is large enough so that it can label the points, a set of points of size 2m in all possible ways, but if I plug in this quantity here, what do I get? Well, what my inequality will tell me, right, is that if the number of samples I see is m is at least to be 2 over epsilon log of 2 to the m, it will be m, if m is at least m over epsilon, something, then something wouldn't happen, right? But this will never be satisfied, obviously. So for this thing to be interesting, what we really need is that at some point, we need that h of m stops behaving like it contains all possible labelings for a sample of size m. Because otherwise, this bound will be useless. Okay, and this is exactly what the VC dimension of the concept class captures. It captures exactly the point at which my hypothesis space h stops looking like it contains all functions. And so in that case, I have a hope to solve for this and to get a meaningful bound here. Okay, cool. And so, right. And so it turns out that there is a VC dimension, and then it will help us clean the bound. Okay, so what is VC dimension? Okay, so now I define, just to use the terminology in Tom's book, because I guess you'll read about this in Tom's book. So to define and to use the classic terminology, so I'm going to say that a set of points S is shattered by H if basically the number of ways of labeling the set S of concepts from my concept class is maximal, is 2 to the size of S, right? That's the maximum I can hope for, right? Because again, there are binary labelings, right? I mean, I can only put plus or minus on each example. Okay, so basically I'm going to say that H shatters the set S if I can label basically the set S in all possible ways by using concepts from my concept space. Okay, so that's the notion of shattering. And now what is the VC dimension of a concept class? So the VC dimension of a hypothesis space or concept class is the cardinality of the largest set S that can be shattered by my hypothesis space. Okay, this is what VC dimension is. And in the case where arbitrary large finite sets can be shattered by H, then the VC dimension is infinite. Okay, so again, basically the VC dimension of hypothesis space H is simply the cardinality of the largest set S that can be shattered by H. So it's the cardinality of the largest set the cardinality of the largest set S that can be labeled in all possible ways by concepts in my hypothesis space. Okay? And let's assume that this is finite for simplicity for the lecture today. Okay, so if this is a definition, and now if I'm asking you guys, yeah?
If such a max cardinality exists, how do we actually find it?
Yeah, so that's an interesting point. We don't need to find it actually, right? Because we are just writing a sample complexity. So our algorithm doesn't need to find it. That's the cool fact, right? So we're just going to use VC dimension to give a bound, right, from the number of training samples. And the algorithm doesn't necessarily need to use the bound. I mean, of course you can go further, and you can also assume that you might also think about, can I use these bounds to design a better algorithm? And that's, I guess, the next question. And yeah, and that's a non-trivial question. That's not, I guess, computationally it's hard. Okay, but typically the way we think about these bounds, really use the bounds for understanding, more for conceptual understanding. If I'm trying to use linear separators in principles, how many training samples do I need? Is it linear in the dimension, quadratic in the dimension, and so on? So if we want to use the bounds just for understanding, and so just for having a first cut understanding of what's the complexity of our learning problem, then the algorithm doesn't need to know what a VC dimension is, doesn't need to know what is the cardinal, right? Doesn't need to find that. Okay, and again, for the lecture today, I just want to think about this simpler case. You're asking all good questions, but I want to first look at simpler cases. Okay, cool. So this is a VC dimension of a hypothesis space H. It's just the cardinality of the largest set S that can be shattered by H. Now, if this is my definition, how do you guys prove, I mean, if I give you a hypothesis space H, like say thresholds or intervals, how do you prove to me that the hypothesis space H has VC dimension of a certain size? I can even tell you for thresholds, the VC dimension is 1. Okay? How would you prove to me that the VC dimension is 1? So what would I have to check? Say it again. Right. So to show that the VC dimension is, say, D in general, 1 for threshold, but D in general, right? First of all, you told me the harder part, but I have to also show a simpler part, which is I need to show that there exists a set that can be shattered, right? There exists a set that can be labeled in all possible ways by classifying my concept space. This is number 1 that I need to show. Okay, and number 2, I also need to show that the VC dimension is strictly smaller than D plus 1. Right? And for that, as you are saying, what I need to show is that there is no set of size D plus 1 that can be shattered. No matter what size D plus 1 I'm trying to choose, there is no way I can get 2 to the D plus 1 labelings. Yeah? This is what you are saying. Cool. So basically, right, so to show that the VC dimension of a hypothesis space H is D, I need to show 2 things. Okay? Number 1 is I need to show a set of points, and just need to show that there exists a set of points, a set of D points that can be shattered, that can be labeled in all possible ways with hypotheses from a hypothesis space. Okay? It doesn't have to be all set of D points, just need to show that there exists a set of D points. Okay, that's number 1. Okay, and number 2, what I need to show is that basically there is no set of D plus 1 points that can be shattered by my hypothesis space. cool. So let's see. Oh yeah, I don't want to give this away. Okay, good. So, okay, let me mention it actually because it's not so. Right, so okay, you can show just by definition, but if H is finite, when the VC dimension, just from the definition of the VC dimension, when the VC dimension of my hypothesis H, if H is finite, is upper bounded by log of the size of H, right? Because obviously if I add here, I cannot shatter log of the size of H plus 1 point because I will need more than size of H hypothesis, right? So when obviously that means that the upper bound, there is an upper bound on the VC dimension, which is log of size of H. Okay, if H is finite. Okay, cool. Now, so let's go through a couple of examples because we have time. And let's see. So, what is the VC dimension of thresholds on the real line? Okay, so maybe we can go through this slowly. So can we shatter 1 point? So what does it mean to shatter 1 point? Right, so if I have 1 point, right, so, oops, okay, I guess right, I'll try to draw here. Okay, so this is my real line, my instance space, and I have this point over here. Can I shatter it? What does it mean to shatter it? To label it in all possible ways. There are only 2 possible ways, right? So can I shatter it? Yes? How? So how do I get a labeling that is plus? Where do I put the threshold? To the left. Yeah, so if I put the threshold to the left, then I can shatter this as being, I label this as being plus, right? If I want to label it as being minus, all I have to do is just to put the threshold to the right, right? So that will be labeling it as minus. Okay, good. So I can shatter, definitely I can shatter 1 point. Now, can I shatter 2 points? Using interval, using threshold.
Yes.
Yes? No?
By just using one.
One, yeah.
So you can say, okay, this one is positive and negative. You can show it this way, but you cannot make it like plus with the same thing. Right? So I think we can.
You think we can by using only one single threshold?
No.
One single threshold. That's all I'm allowed to use. So plus minus, exactly, right? So if there is no way for me to get, so I mean, if I have 2 points, to shatter them I need 4 labelings, but here's a labeling of these 2 points that I cannot obtain, just plus, I mean, this is one labeling is not achievable, right? Because if to get this point as, to get this point as plus, to get this specific point as plus, I'd have to have the threshold here, but if I put the threshold here, then this will be plus 2. Okay, so very simple reasoning. Okay, so basically, this shows that the VC dimension of this, I guess the VC dimension of threshold functions is 1, because there is no set of size 2 that can be shattered, and I can shatter, there exists a set of size 1 that I can shatter. Okay, how about the VC dimension of intervals? So, any guess here? So can I shatter 1 point? I can shatter everything? Wow, that would be cool. If I can shatter everything, that means also, I mean, I would be very worried though if I can shatter everything, right? Because then that means, like, no matter what, that means that somehow I need to see a lot of things too. I would never have any hope to achieve learnability. Yeah, so if I could really shatter anything, a set of arbitrary size, then that means that basically my hypothesis space doesn't have any structure. And so I cannot hope to achieve any generalization guarantees. Right? But then this hypothesis space, I mean, intervals, they look kind of restricted though. And we know, when we did a computation for the shattering coefficient, we noticed that it's only kind of m squared, so it doesn't behave like in a wild way. Okay, so any guess of what is the VC dimension here? You think it's 3? Okay, cool. So 3, okay. 2.
Plus minus plus the count.
Okay, yeah, that's the answer. So I guess if you guys answer lots of questions, you get bonus points. Okay, right, so Terry, yeah, you said you are Terry? Yeah, so Terry is right. So basically, so the VC dimension is not quite 3, it's 2, right? So you can actually verify that, right? So I mean, I didn't write it here, but you can easily verify. So first of all, that there exists a set of 2 points that can be shattered. I can just take 2 distinct points, and then I can show that I can shatter them, right? To get the labeling plus on these points, what do I need to do? Where do I put my endpoints? To label both of these plus. What interval would I label plus? I mean, if I put the interval here, obviously I can get plus, right? If I want to get this one minus and this one plus, I can just put the interval here, the other way around, right? And if I want to be minus, I can just put it here. Okay, good. So, but on the other hand, I cannot shatter these 3 points. Right, so no set of 3 points can be shattered, and in particular, there is this configuration plus, minus, plus that I cannot achieve via an interval. Simply because to achieve these two guys as being plus, I need to have the interval here, but then this will be labeled minus. Okay? So the VC dimension here is 2. Okay? Now, how about the VC dimension of, so let's think about another question. How about the VC dimension of union of k intervals? Now, so we looked at one interval. Okay, how about now union of k intervals? So now we have, guess k intervals. Okay, what is the VC dimension here? So here I have 3, k is 3. So it looks like a more complex class of functions. So any guess on what's the VC dimension? I mean, that's a nice thing about VC dimension, that you can compute it. I mean, like, I guess analytically you can compute it, and you then know exactly how many samples your algorithm would need. Yes? K plus 1. I think, okay, so k is at least k plus 1. Yeah, so I would agree it's at least k plus 1. I think it's a bit higher though. Can we shatter 2k points? If I give you 2k points, can you shatter them? So how would we shatter 2k points? What's the argument that we can shatter 2 times k points? Okay, so I guess it's written there, right? So we can definitely shatter 2 times k points. And how can we shatter them? Well, I mean, the easiest way to think about it is to pair them up. And then for every single pair, we can use one interval, right? And we know that with one interval, we can label any 2 points in all 4 possible ways. And so therefore, if I have 2k points on the real line, I can just pair them up. I can use one interval for the first pair, another interval for the second pair, and so on. And so I have k intervals for k pairs, and I'm going to be able to achieve all possible labelings. So it's via reduction to intervals. Okay? So I can shatter 2k points, but can I shatter 2k plus 1 points? Yes? No? No. Why? Plus, minus, plus, minus. Okay, perfect. So, okay, I should actually have a plus here too. So I have 2k plus 1 point. Actually, let me edit. Right, I should have, yeah. So why can't we shatter this? Oh, sorry, why can't we get this configuration? Okay, good. So, okay, to argue that we cannot shatter 2k plus 1 points, we need to put 2k plus 1 points down, and we need to show a labeling that we cannot achieve with concepts from our concept space, right? And as you're saying, the labeling that I cannot achieve is this one over here, where I have plus, minus, plus, minus, plus. And why is it so? Why can't I achieve this labeling? What's a quick argument for that? I would need k plus 1 disjoint intervals because I have k plus 1 pluses, right? I need k plus 1 disjoint intervals, right? And I have minuses in between, and I'm not going to have so many k plus 1 disjoint intervals because I only have k intervals in my concept space. Okay, cool. So the VC dimension of unions of k intervals is 2k. Now, let's actually talk about something that we even care about more. So, I mean, intervals, thresholds are just examples to start, to help us start thinking about the concept. But let's pick something that is more useful in practice, and let's think about linear separators, right? Because we've seen linear separators are widely used. Now, I can tell you that the VC dimension of linear separators in RD, okay, I'm not going to tell you actually what it is. I'm going to ask you. Okay, so what's the VC dimension? Any guess for the VC dimension of linear separators in R2? Yeah? 3. Okay, perfect. Why?
Like you draw 4 points.
Oh, you are telling, you are telling me right now why it's not 4. Okay, but you.
So first I know it's impossible for 4 points.
Okay, good. Why is it impossible for 4 points?
You draw 4 points in a square, at each corner.
Yes.
And you put the, for each diagonal, for each 2 points at the diagonal, use the same label.
Yes.
And in this case,
is impossible.
Yeah, so you're totally right, okay? You're totally right, but then you want to show to me is that there exists a set of points that I cannot, you are telling me that you argue that there exists a set of 4 points that I cannot shatter. But I also need to know that no set of 4 points can be shattered. In order to show that the VC dimension is not 4, is strictly smaller than 4, I need to show that there is no set of size 4 that can be shattered. You told me that if I put a square, like the points, right, at the corners of the square, those points cannot be shattered. But what if I give you a different set of points? Okay, so you argued, actually, I have a picture here, right? So the case that you argued is this one over here, right? I mean, if I put this like in the corners of the square, right? So what your colleague was arguing, what's your name? Ing. Okay, what Ing was arguing is, so he was trying to, so he, actually, it's very good progress. I mean, it's almost, it's great. Good, so I guess what you're arguing, so he was trying to argue that the VC dimension of linear separators in R2 is strictly smaller than 4. Okay, this is what he was trying to convince us. Okay, and so basically he was working on the harder case, which is showing that there is no set of size 4 that can be shattered. So there is no set of size 4 that can be labeled in all possible ways of linear separators in R2. Okay, now he was doing the second case over here. So there are 2 cases to think about. One of them is, basically the one case would be when none of the 4 points is in the convex hull of the others. Okay, if none of the 4 points is in the convex hull of the others, then I can easily show that I cannot, there is a labeling of these points that I cannot get to linear separators. And in particular, like in this picture over here, I'm going to label these diagonally opposite points in the same way, maybe plus, plus, and these 2 guys minus, minus. And if you think about it, there is no linear separator that achieves this labeling. Okay? Because if it does so, it would have to somehow label the point at the intersection of these diagonals as both plus and minus, and that's impossible. Okay, so that's one case where there is no, none of the 4 points is in the convex hull of the others. And so there is a labeling I cannot achieve in that case. There is another case to think about, which is what if there is a point in the convex hull of the others? Okay, because I need to rule out any set of any possible sets of 4 points. Okay, but that case is even easier. Okay, if there is a point in the convex hull of the others, it's even easier because there is a labeling I cannot achieve, namely labeling these guys. So these guys over here plus, right? So, and the point inside the convex hull is minus. There is no way to achieve this with a linear separator. Right? Because if I know if I have a linear separator, anything in the convex hull of these 3 points, if I have the same labeling, we have the exact same labeling by convexity. Okay, so basically the VC dimension, so we argued that the VC dimension of linear separators in R2 is no bigger than, is strictly smaller than 4, because there is no set of size 4 that can be shattered with linear separators. Okay, but we also need to show, in order to complete our argument, we need to show that there exists a set of 3 points that can be shattered, that can be labeled in all possible ways. And that's the easy part, actually. So typically, this is the easiest part. I mean, showing that there exists a set of size D that can be shattered is typically the easier part. And even here, you can just pick any 3 points that are not collinear. And then you can argue that for every labeling, there is a linear separator that will give me that labeling. Okay, do you guys believe this? I mean, you can just play with it and you proceed. Okay, so the VC dimension of linear separators in R2 is 3. Okay, do you guys have a conjecture for the VC dimension of linear separators in RD? Because this is a really interesting case, right? This is when we start touching on algorithms like logistic regression, SVM, and so on. So any conjecture? Okay, I'm going to tell you. So it's D plus 1. Okay, so and this proof is actually it's quite really interesting again. So it uses a bit of convexity and geometry. And I'm going to put it as a extra credit homework question. Okay, so it turns out that you can argue that the VC dimension of linear separators in RD is D plus 1. So it's only linear in D, which is great news. Okay, cool. So now this is about VC dimension. I need to make sure I go through my whole story. Okay, so now as you see, the VC dimension is a nice combinatorial quantity to think about. We can compute it for concept spaces that we care about, right? But now I want to go back and talk about how is VC dimension showing up in our sample complexity result, right? And and here is actually a useful fact, a very interesting fact. Again, it's not easy, it's not hard, but not trivial to prove. It will take me a lecture to prove it. Okay, so here is a very useful fact about the VC dimension. It's something called the Sauer's lemma. So it turns out that the VC dimension has a very, very interesting property, okay, which is stated on the slides. And so let me Okay, so it turns out that basically the VC dimension is exactly the moment where the shattering coefficient transitions from being exponential to being polynomial. Okay, this is intuitively speaking. And now let me go through this, what do I mean? Now, if m, the number of points, is more than or equal to the VC dimension, when I claim that h of m, the shattering coefficient, which is the maximum number of ways of splitting m points of concepts from my concept space, right? If m is more than or equal to d, the VC dimension, then I claim that h of m is 2 to the m. Do you guys believe that? It should be. Why is it so? So what is the definition of VC dimension? It's the cardinality of the largest set of points that I can shatter, right? And so by definition, because I can shatter a set of d points, it's the cardinality of the largest set of points that I can shatter, that means that for any m smaller than or equal to d, there will be a set of size m that I can shatter. So therefore, the shattering coefficient here will be, right, h of m will be 2 to the m. Okay, that's obvious by definition. Now, the very interesting fact is that when once m becomes strictly greater than d, then the shattering coefficient will stop being exponential, will stop being 2 to the m, and will only be order of m to the d, which is polynomial. Yeah, so that's very interesting. So that's what VC dimension is. Exactly the moment when the shattering coefficient transitions from being exponential to being polynomial. Okay, now why is this interesting? Because going back to my sample complexity result, why is this interesting? Because what I really care about is to get a sample complexity result. Well, it's interesting because if you remember this very first fact that we said that we can replace h, size of h, when h is finite, with this shattering coefficient over here, right? And we played with it and we said, well, if the shattering coefficient is like 2 to the m, it's like if I can shatter, for a set of size m, I can shatter all points, then this inequality will never going to be satisfied. Right? So for this inequality to have any sense and to be even satisfied for a finite sample size m, I need that h of m, it cannot be exponential. Because when I take log, I have linear in m. I have m on both sides, is no good. But if the shattering coefficient suddenly becomes polynomial, like m to the d, where d is the VC dimension, then it turns out that I hope for solving this. And in particular, what happens, actually, right? So what will happen then, right? So if I have a value of m for which the shattering coefficient, instead of being exponential, now is polynomial, what will happen when I take the log, I'm going to have if m, what the inequality, this inequality will tell me, if m is greater than, will be, I'm going to ignore the constant, it will be like 1 over epsilon, and what will be log of m to the VC dimension of h. What is that? Is VC dimension of, yeah, what is that? VC dimension of h times log m, plus some other factors, okay, but I'm going to ignore for now. But now what's the interesting fact here is that I have an inequality that is actually solvable, because I only have, if m is greater than 1 over epsilon, this dimension of h times log m. So log m here is much, much smaller than m. So it turns out that I can actually go ahead and solve this inequality, and I can come up with a sufficient condition on m that ensures that this inequality is true. And in particular, the sufficient condition is written over here on the last theorem. So basically what we can show by using this reasoning is that if the number of samples that we see in the training phase is of the order 1 over epsilon times VC dimension of h times log 1 over epsilon plus log 1 over delta, then the same statement we had before, with very high probability at least 1 minus delta, all the bad hypotheses of true error rate at least epsilon will be inconsistent with the data. Okay, so we get a nice sample complexity statement that looks, it only depends on this VC dimension notion, which is nice and easy to think about, and you can have fun computing. Yeah, so this is a general statement for the case when the class of functions h is not finite. So when the class of functions h is not finite, it turns out that we have these very interesting sample complexity statements that depend on the VC dimension of the concept class, right? And for example, the statement that I wrote here applies to any consistent, so applies to any algorithm that outputs a consistent classifier, right? It can be logistic regression, it can be ID-free, as long as what they output at the end of the day is a classifier that perfectly correctly labels a training sample, right? It's a very generic algorithm, right? And what this bound tells me is how many samples do I need to see as a function of the complexity of the output space in order to get good generalization guarantees. This is for the realizable case. One can also extend that to the agnostic case. One can extend the same statements to the case where the target function might not be in the class. Okay, any questions? Right, and actually maybe just to go one more slide here. Basically, the key point what made VC dimension so interesting is basically it's exactly the moment when the shattering coefficient stops being exponential and transitions in being polynomial. And that's cool because then this implies learnability guarantees, according to the reasoning that I mentioned. Okay, cool. So now, actually let me go, mention this. Okay, I want to go through this because I already said it, but let me say it again, right? So we now have this very, very generic sample complexity statement. We know that the number of samples we need to learn well is only 1 over epsilon VC dimension of h times log 1 over epsilon plus log 1 over delta, right? Now we can now plug in, we can pick concrete classes of functions and plug in, see what is the VC dimension, how many samples do we need in order to learn well, right? And we've already went through the case on the class of functions is linear separators in our D. I mentioned that the VC dimension then is D, right? And what this bound then implies is that if the number of samples that I see is linearly in D, the dimension, only linear in 1 over epsilon, then I get good generalization guarantees, or epsilon is my desired target error. Okay, so that's really interesting actually, because now we know how many samples we need in order to generalize well if we apply logistic regression, or SVM, which will be an algorithm that we analyze later, or perceptor. Right, so that's very broadly applicable actually. This is a real strength of these results. They are very generic, they're just, they're unbelievably useful and interesting. Cool. And so I guess also just to spell this out, like so, what, for example, here, right? This also tells us the dependence, how the dependence, if we are trying to learn linear separators in RD, how the dependence on D comes into the bound. It's only linear in D. So, for example, if we double the number of features, then I only need to see roughly twice more samples in order to get the same generalization guarantees. Okay, so we can then understand how should we increase the number of samples as a function of increasing the complexity of the search space, maybe increasing the number of features or the complexity of the search space more generally. Okay, cool. And actually also, let me also mention, so because it's important, whenever you see an upper bound, so this is an upper bound. The way I stated it, I said, well, if you see VC dimension over epsilon, number of samples, that's sufficient to get good generalization guarantees, right? But you might ask me, okay, is this a very loose upper bound? You know, how close is to the best we can hope for? And it turns out that this is a question that is, again, well studied. And this is almost tight, in the worst case, over the choice of the target function over the choice of the underlying distribution. This is almost tight. Basically, it's tight up to a log 1 over epsilon factor. So the only thing that we don't know if it should belong to the bound is this log 1 over epsilon factor. Right, so it's almost tight up to this log 1 over epsilon factor. We don't know if it belongs there or not. And right, so basically, I'm not going to go through the proof, but one can also prove that for any hypothesis space H, for any algorithm, so that's an information theoretic lower bound, we can prove, which says that for any hypothesis space H, for any algorithm, for any accuracy parameter epsilon, for any confidence parameter delta, there exists a distribution and a target function, so that if my algorithm sees fewer than VC dimension over epsilon samples, then with probability at least delta, my algorithm will output something of error at least epsilon. So I'm not going to achieve kind of the learnability guarantees that I would like to. Okay, and so basically this almost matches the upper bound up to this log 1 over epsilon factor. And in general, it's not known if the log 1 over epsilon factor belongs there. It's a big open question, actually, in learning theory. It has been around for, I think it's the 70s or so. In my recent work, I was able to get rid of this log 1 over epsilon for the class of linear separators. So progress can be made. Okay. But in any case, from the point of view of this class, it's, what this says, what actually this pair of bounds, upper and lower bound, shows that really VC dimension is the right notion of complexity that characterizes the sample complexity of a learning problem. Okay, and notice that this notion, this bound applies in worst case over the choice of the distribution over the feature space, worst case over the choice of the target function. So no matter what is the fixed underlying distribution over the feature space, no matter what is the fixed underlying, the fixed unknown target function, if I see so many samples, I'm guaranteed that if I find something that's all over the sample, I'll do well in the future. Cool. And so let me actually, I'm not going to go through the lower. Actually, the lower bound proof is not very hard, but I'm going to skip this. It's actually because I'm almost out of time, but it's not really hard. We just at a high level, what we do is just pick a set of points that can be shattered, and we put a lot of weight on one of the points, and then we spread out the weight on the remaining points, and then we can argue that unless I see half of the remaining points, I'm going to have error at least epsilon. But in order to see half the remaining points, because the remaining points have so small weight, I need to roughly see d over epsilon examples. Okay, so that's actually a very simple way to even think about the lower bound proof. It's not really hard. It holds for kind of a skewed distribution. Okay. Okay, cool. So I guess I'm almost out of time, so let me just mention. So discussion so far, and was mostly for the case when the target function does belong to the concept space, because in that case, this theorem was meaningful. I mentioned this last time, that the target function does not belong to the concept space, so it turns out we can provide very similar bounds, where now the bound is a bit different. What we're going to argue is that if the number of samples is large enough, then uniformly for all functions in my concept space, I'm going to have it their empirical error rate is within epsilon over true error rate. Okay, and then the bound will have a certain form. It looks almost the same. So when h is finite, it looks almost the same, except that 1 over epsilon gets turned into 1 over epsilon squared. So it's quadratic dependence on epsilon now. Okay. This is for the case when h is finite. And we can get something very similar when h is not finite by just replacing basically size of h, log size of h with VC dimension of h. Okay, and the proof of these results are beyond the scope of the course, I guess. In order to prove this, we're going to need to use some tail bounds like Hovding inequality. I have them on the slides if you're curious, but it's not something that you are required to know. Okay, and let me just stop here. Okay, so from the point of view of, I guess, of this lecture, what we really want, the last couple of lectures, what we really want to know is the notion of sample complexity. What does it mean? Why is it important? Why do we care about sample complexity? Right? Because obviously we care about algorithms that generalize well, and sample complexity can help us formalize this and think about what that means formally, probably. Okay, and actually I think it would be, I think that this is required for you guys to understand the reasoning behind the simple sample complexity bound when h is finite. It's the simplest probabilistic argument that I know, but it's very insightful, so I'd expect you guys to know that. And also from the lectures today, what is important to understand is the notion of VC dimension, shattering, and so on, in the form of the bound. So the proofs are not required. Okay, cool.